Welcome everyone, I'm Christian Winter and I'm here today to present our work GeoBlocks, a query cache accelerated data structure for spatial aggregation over polygons. This is joint work with Andreas Kipf, Christopher Nesa, Eleni Tsirita Zacheratu, Thomas Neumann and Alfons Kemper. I want to start off with a little introduction into spatial aggregation for those not familiar. So in spatial aggregation, we deal with distributed points. Each of these points has latitude and longitude location and additional info attached to it. For example, if we might deal with houses, we have something like the house price and the square footage. When querying these points, we're usually not interested in single information points, but want to extract information over a whole area. For example, a German county. And for this, we might want to know the average area of houses or the maximum price or so on. Now, checking this manually by, for each point, testing if it's contained in the polygon and aggregating it and adding it to the result if so, is very tedious and slow. So there are obviously already solutions for this. Most work by first building a spatial index structure, like a quad tree or displayed here an R tree, on these points. Parts of these index, for example internal nodes of the R tree, are then pre-aggregated and the information of all points stored within is annotated at this node. Now, when we query this index structure, we can discard the points and simply focus on the index structure. So we first approximate our query polygon as needed, for example rectangular for the R tree, and then query it. And when encountering a node of the R tree, we then, on our way down, we then include it in the result if necessary. So by this we already achieve pretty high throughput and low query latencies, but you can already see here that the approximation is a bit problematic. As the index is built based on the distribution of the points and not the query polygon, the result cannot really be error bounded. Furthermore, we have some additional problems with overlapping nodes, which requires expensive reassignment. So the current approaches already have this low query latency we want through pre-aggregation. So we obviously want to keep that as well for our approach. But you saw that the rectangular approximation in the beginning of the polygon can be problematic, and we have to deal with issues like overlapping nodes in parts. These require additional refinement, which often accesses the raw data, and this is therefore slow. So we want to avoid that if possible. And you also saw that we cannot guarantee error-bounded results, which we want to achieve for our work. So what does this mean? We want to keep the pre-aggregation, but for our approach we need to rethink the indexing. Next, I'll give you a high-level overview of GeoBlocks. For the technical details on how everything works, I'd like to refer you to our paper. As I said, we need to rethink the indexing. What does this mean for us? Well, the indexes like the R tree and the quad tree are data dependent. This is an advantage in some way because it automatically adapts to the workload and we have higher resolution in densely populated areas, but this also means we have worse resolution in sparsely populated areas. This is problematic when we're looking for error-bounded results. So instead we used a fixed size grid that we overlaid our points with. We then pre-aggregate all cells contained within a grid like we did for R3 internal nodes in the competitor section. This now has already two advantages. For one, we're not dependent on the resolution, so each cell is fixed sized and so we have similar granularity throughout the grid. Furthermore, we don't have any overlaps as we can perfectly align the grid, and therefore we have no need for refinement. This already checks the first box of what we want to achieve. Now to look at how we achieve error-bounded results, we have to look at geoblocks queries. For queries, we, as a first step, need to map the query polygon to grid size. You can already see here that we can much more closely approximate the query polygon with our grid size. We can even incorporate details like gaps in the polygon in the middle here. Now, once we have this approximation, we need to overlay it with our data with the pre-aggregated cells that we have of the data. So then we can check, do we need this grid cell for the query, and do we even have aggregates for this? So is there even data for this? If both holds true, we combine the grid cell with the others, which also fulfill this condition, to get the final query result. Now you can see that this approximation is for beta, and this approximation even allows us to guarantee error-bounded results. Because when looking at the grid cells in more detail, you can see here that at the very worst, which is almost the case for the middle right section, the error is a grid cell diagonal. But in reality, top left, it might be more the case that we already have a partial overlap anyway, so the average error is even lower than that. And as the user can define the grid size at creation time, this is even a user controllable bounded error. Now, we also saw potential of further speeding this up by noticing that polygons are often not fully changed between queries, but just resized or reshaped around the borders. So when keeping track of commonly queried areas, for example, the red, green, and orange boxes here, and tracking how often they're queried, we can further aggregate these often queried areas and cache them. Now, when we have these cached results at coarser granularity, we can reuse them if all cells are required again. So how does this perform then in regards to speed and error-bound results? For this, we compare it to three competitors here: a B tree, a regular index structure on our grid cells, which we enumerated; the pH tree, a multidimensional index structure, which we use on the points. Both of these are on-the-fly aggregation, and we also use the AR tree, which is very similar to the competitor approach outlined in the beginning, where it keeps aggregates for inner R-tree nodes. We evaluate this on two datasets: New York City taxi rides and tweets within the US. Focusing on the runtime for different selectivities, for which we generated random polygons within New York City that contain a certain amount of rides, you can see that the pre-aggregating approaches on the bottom far outperform the on-the-fly aggregation, often by orders of magnitude. Please also notice the log scale on the y-axis. We further see that geoblocks are best for low selectivities, and that our query caching, the purple curve, really pays off throughout the board. And in addition, you can see that we are always competitive against the AR tree. So then focusing on runtime and accuracy, we query the Twitter dataset with the US states and randomly generated rectangles. You can see that the geoblocks accuracy and performance is really independent of the query workload. Furthermore, you can see that the pH tree suffers from the rectangular approximation of the states in accuracy, which is not the case for rectangular queries. Our version of the AR tree suffers from missing refinement of overlaps and so on for both cases. Now you can see that geoblocks is really here best overall, offering the best compromise of performance and error in the result. To sum up, we achieve the sub-second query latencies required for interactive analysis by pre-aggregating and by reusing commonly queried areas. We can achieve error-bounded results without need for refinement by using a non-overlapping fixed-size grid as an index structure for our work. Thank you for your attention.